Welcome to this video supplement dealing with complex number arithmetic. We are going to consider 4 problems where we have to evaluate some complex expression. Before we go to any of them, let's keep 3 big ideas in mind. The first of which is that I squared is equal to -1. That's based on the definition of the imaginary number. Secondly, if we're multiplying 2 items together that have the same base, how this works is we keep the base the same and we add the exponents. So x to the 4th times x to the 3rd will be x to the 4 plus 3, which is 7. And the third item is what happens if we have an expression with what could be viewed as a double exponent. In this case, if we have x to the 4th all being cubed, the base stays the same, it's still x, and we multiply the exponents together to get our new exponent. 4 times 3 is 12, so this would be x to the 12th. Keeping those 3 items in mind, let's look at our first problem, 5i to the 11th. So what we're going to do is split I to the 11th into the product of 2 I terms. From one of them, we want the largest even integer that we can subtract off from 11, and that's going to be 10. So if we think about our property here, I to the 10th times I to the 1st would be I to the 11th. And now we're going to rewrite I to the 10th as I squared to some exponent. And I to the 10th would be I squared to the 5th, because 2 times 5 is 10. Well, now we're going to replace I squared with -1, because I squared is equal to -1. A -1 to an odd exponent is going to be -1, because you have a negative times a negative times a negative times a negative times a negative. With an odd amount of negatives, the answer will be a negative. So 5 times -1, and we still have the I. 5 times -1 is a -5, and then we have the I at the end. So 5i to the 11th simplifies to -5i. Let's go to our second problem. -3i to the 18th. Again, we're going to simplify this, but I to the 18th is already the largest even exponent that we can split it into. So what we'll do next is rewrite I to the 18th as I squared to some exponent. In this case, it'll be I squared to the 9th, because 2 times 9 is 18. We know that I squared is equal to -1, so we'll replace I squared with -1. A -1 to an odd exponent is going to be a -1, and -3 times a -1 is a +3. So the answer to -3i to the 18th is that it simplifies to be +3. Let's consider the next problem. Now in this case we have an imaginary term in a denominator, but we're going to think about it the same way. So I to the 12th is already even. We're going to try to write it as I squared to some exponent. Well, 2 times 6 is 12, so I squared raised to the 6th is really I to the 12th. Now we'll go through and we'll replace I squared with -1. A -1 to an even exponent would be positive, because a negative times a negative is a positive. So this will be 4 over 1, which is just going to be equal to 4. And we have one more problem that we will consider. 7 over I to the 23rd. So first of all, in the denominator, we're going to split I to the 23rd into the largest even number that we can subtract, which is 22, and then it'll be times I. Now I to the 22nd we will rewrite as I squared to some exponent, and that exponent is going to be the 11th. 2 times 11 is 22. I squared, we can replace it with a -1, because I squared is equal to a -1. We keep the 11, multiplying by I. A -1 to an odd exponent is going to be a negative number, and we can just bring that negative out front of our fraction, so this will turn into negative 7 over I. But we can't leave the I in the denominator, so in this scenario we would have to multiply by I over I. This will give us a negative 7I all over I times I is I squared. Replace I squared with negative 1, and a negative times a negative, or a negative divided by a negative, however we want to look at it, is a positive. So overall, the answer for this item would be 7I. And this is basically how we work with imaginary numbers to exponents larger than 2. We split it into an even exponent that we look at as I squared to some new exponent, and then just an I added on to the side. Keep that in mind, and these problems might not be as complex as initially perceived.